Tonight, a cosmic mystery unfolds in one of the strangest corners of the universe. More than 100,000 stars seem to have vanished, but the truth is far more surprising than a simple empty void. This is not really the story people think it is, and it does not begin in the famous Boötes Void at all. It begins with how astronomers count stars, how galaxies tear smaller systems apart, and how the sky can hide what is still there. Before we begin, please like the video, subscribe to the channel, and join us as we uncover one of the quietest and most fascinating mysteries in modern astronomy. In the largest view that present observation allows, the universe spreads outward in a pattern that is neither random nor uniform. It arranges itself in a vast network known as the cosmic web, where matter gathers along extended filaments and collects into dense knots, while wide regions between them remain comparatively empty. Galaxies trace these filaments like faint lights along branching paths, and clusters form where several paths meet. Between these luminous strands lie voids, immense volumes where few galaxies reside. This structure emerges gradually after the early expansion of the universe, shaped by gravity acting over long spans of time, drawing matter together in some places while leaving other regions thin and diffuse. Within this framework, the idea of absence must be treated with care. A report that many stars have vanished cannot be understood at the scale of the cosmic web alone, because individual stars are not spread evenly across intergalactic space. They belong to galaxies, bound by gravity into systems that contain gas, dust, and dark matter. The web provides the broad architecture, but it does not hold stars in isolation. Any account of missing stars must therefore begin by locating where those stars would naturally reside within this structure. Observations of the cosmic web come from large surveys that map the positions and motions of galaxies across vast distances. These surveys reveal patterns extending across hundreds of millions of light-years, where clusters appear as dense concentrations and voids as wide gaps. The light from distant galaxies travels for long durations before reaching detectors, carrying information about the distribution of matter at different stages in cosmic history. From this data, astronomers reconstruct a layered picture of structure, one that changes gradually as the universe expands and evolves. In this broad context, a void is not a complete absence, but a relative one. Even in the emptiest regions, a small number of galaxies may still be present, though widely separated. The density of matter there is far lower than in filaments or clusters, yet not strictly zero. Gas remains. Dark matter extends through all regions, and faint galaxies can be detected with sensitive instruments. The term void describes a contrast rather than an absolute condition. It marks where matter is less concentrated, not where it ceases to exist. The cosmic web also reflects the influence of dark matter, a form of matter that does not emit or absorb light but reveals its presence through gravity. Dark matter shapes the growth of structure by providing the gravitational framework within which ordinary matter gathers. Galaxies form inside halos of dark matter, and these halos trace the same filamentary network seen in the large-scale distribution. Without this unseen component, the web would not take its observed form. The presence of dark matter ensures that even regions appearing empty still contain mass, guiding the motion of galaxies and the flow of gas. Within such an arrangement, stars are confined to the densest environments. They form in clouds of gas inside galaxies, where gravity compresses matter until nuclear fusion begins in their cores. Once formed, stars remain bound to their host systems unless disturbed by strong interactions. The cosmic web does not directly host stars in isolation across its vast spans. Instead, It determines where galaxies form and how they cluster, indirectly shaping the environments where stars can exist. Because of this layered structure, any report involving a large number of stars must be interpreted at the correct level. A claim that 100,000 stars have vanished does not align naturally with the scale of voids or filaments. At those scales, astronomers track galaxies and clusters rather than individual stars. The counting of stars occurs within galaxies, where distances are smaller and individual objects can be resolved or inferred through careful measurement. The light that reaches telescopes carries signals from many layers at once. Nearby stars appear as distinct points, while distant galaxies blend into faint smears. Instruments must separate these signals through resolution, sensitivity, and repeated observation. Errors or limits in these processes can lead to apparent differences between surveys, where some objects are detected in one dataset but not in another. At the scale of the cosmic web, however, such discrepancies are not described in terms of individual stars but in terms of galaxy counts and distributions. The expansion of the universe adds another layer to this view. As space itself expands, distant galaxies move away, and their light shifts toward longer wavelengths. This effect, known as redshift, allows astronomers to estimate distances and construct three-dimensional maps of structure. The farther a galaxy lies, the earlier in cosmic history its light originates. This creates a layered record where the web can be studied across time as well as space. Yet even in this deep perspective, stars remain components of galaxies, not independent markers across the void. In considering a cosmic mystery, the distinction between scale and object becomes essential. A missing set of stars must be examined within the systems that contain them, not within the broad emptiness between galaxies. The cosmic web provides context, showing where matter gathers and where it thins, but it does not offer a mechanism by which large numbers of stars would vanish from observation without leaving corresponding changes in their host galaxies. Observations indicate that the large-scale structure of the universe remains stable in its general pattern over long periods, evolving slowly as gravity continues to shape the distribution of matter. Voids expand slightly as matter flows outward toward denser regions, and filaments grow more pronounced as galaxies cluster. These changes occur gradually and do not involve the sudden disappearance of stars. Instead, they reflect the ongoing redistribution of matter on the larger scales. It remains uncertain how every detail of the cosmic web formed from the earliest conditions of the universe, and simulations continue to refine the understanding of this process. However, the broad agreement between observation and theory supports the view that structure grows through gravitational attraction, acting on initial variations in density. Within this framework, stars are secondary elements, formed later inside galaxies that themselves trace the underlying web. This outermost region of the topic establishes a foundation. It shows that the universe is structured, that emptiness is relative, and that stars belong to localized systems rather than to the vast spaces between them. With this understanding, the idea of vanishing stars can be set against the proper scale, preparing a gradual movement inward toward the environments where such a claim can be meaningfully examined. A cosmic void is one of the most misunderstood structures in astronomy, because the word itself suggests a complete emptiness that does not actually exist. In scientific use, a void is a vast region of space where galaxies are much less common than expected when compared with the cosmic average. It is an underdense region, meaning a place where matter is present in lower concentration, not a blank hole cut out of the universe. Even the most famous examples contain some galaxies, thin gas, dark matter and radiation passing through. They look empty only by contrast with the richer surroundings where galaxies gather into filaments, walls, and clusters. The Boötes Void is one of the best known of these regions. It lies in the direction of the constellation Boötes and extends across an immense volume of space, often described as roughly 250 to 330 million light-years across, depending on the method used to define its boundaries. Those boundaries are not solid edges. Like many structures in astronomy, they are statistical. Astronomers map where galaxies appear, compare the density of one region with nearby regions, and describe a void where the count drops far below the norm. The Boötes Void is therefore not an object with a clean surface, but a broad, thinly populated region within the larger cosmic web. This distinction matters because the void is about galaxies, not about individual stars. At the distance of the Boötes Void, astronomers do not count ordinary stars one by one. Those stars belong to remote galaxies too faint and too small on the sky for such direct counting in most cases. What surveys reveal there are galaxies as whole systems, each containing millions or billions of stars. So when popular language describes stars vanishing in connection with a void, the scale is already slipping. A void is identified because fewer galaxies are found inside it than expected, not because astronomers once saw individual stars there and later watched them disappear. The Boötes Void gained attention because it seemed strikingly large for its low density. When it was identified in the early 1980s through redshift surveys, it stood out as a dramatic example of large-scale structure, not merely a gap between clusters, but an immense region with far fewer galaxies than surrounding space. Later observations found that it is not totally empty. A number of galaxies do inhabit the region, though still far fewer than a similar volume in a denser part of the universe would hold. This is typical of voids in general. Their emptiness is relative, and careful observation nearly always reveals some scattered occupants. Inside such a region, conditions differ from those in crowded galaxy environments. Galaxies in voids are more isolated, with fewer close encounters and fewer large neighbours exerting strong gravitational influence. This affects how galaxies grow, merge, and consume gas. In denser environments, repeated interactions can disturb structure, trigger bursts of star formation, or strip gas away. In a void, a galaxy may evolve more quietly. Yet this relative isolation does not mean the laws of physics change there. Gravity still works, gas still cools and forms stars under the right conditions. Dark matter still shapes the distribution of matter. A void is sparse, not strange. Because the Boötes Void has become culturally famous, it often attracts exaggerated interpretations. It is sometimes described as though something swept matter away from the region, or as though an unknown force erased galaxies from space. Current evidence does not require such ideas. In the standard picture of cosmic structure formation, voids arise naturally as matter flows over immense spans of time toward denser regions. Areas that begin slightly less dense than average lose material gradually as gravity amplifies the contrast between dense and sparse zones. Filaments become richer, clusters become heavier, voids become emptier by comparison. The result is dramatic, but it follows from known processes acting over cosmic time. This helps explain why the Boötes Void is not the right place to anchor a mystery about 100,000 vanished stars. The famous puzzle of the void concerns the large-scale distribution of galaxies, not a measured loss of resolved stars. The missing quantity, if one wants to use that word carefully, is a shortage of galaxies relative to expectation inside a huge region of space. Even then, The shortage does not mean galaxies were once definitely there and then removed. It means the region ends up with fewer galaxies than a comparable volume elsewhere. That is a very different scientific statement. The difference between expectation and disappearance is important. In astronomy, expectation often comes from models, averages, and comparisons across many surveyed volumes. A region can be surprising without implying a sudden event. The Boötes Void is surprising because it is very underdense across a large span, not because telescopes recorded a rich field of galaxies there and later found darkness. The language of vanishing can mislead by turning a structural contrast into a dramatic subtraction. It also remains important to remember that even a void is not dark in every sense. Light from foreground stars crosses it. Background galaxies shine beyond it. Radiation from the wider universe passes through it continuously. Dark matter occupies it. Thin intergalactic gas persists in low density. The emptiness is measured against the usual abundance of galaxies, not against absolute nothingness. This is one reason astronomers prefer precise terms such as underdensity, galaxy distribution, and large-scale structure. Those terms sound less dramatic, but they describe reality more faithfully. Observations continue to refine the internal structure of voids, including how many faint galaxies they contain and how their shapes connect to surrounding filaments. It remains uncertain exactly how every large void reaches its final observed form, because the details depend on initial conditions, dark matter behavior, and the long history of matter flow. But there is strong agreement on the central point. A void is a sparse region in the cosmic web, not a place where stars individually vanish from the sky. In this outer scientific sense, the Boötes Void stands as a lesson in scale. It belongs to the architecture of the universe, where the main units are galaxies and the spaces between them. It is immense, quiet, and comparatively poor in matter, yet still part of the same cosmic pattern seen across the observable sky. To understand a claim about vanished stars, the mind must remain disciplined here. The void is real, but it is not the scene of that particular mystery. It is a famous emptiness of one kind, while the deeper question belongs elsewhere, in regions where stars are counted more directly and where absence can take on a more exact meaning. The movement away from the Boötes Void begins with the simple correction of scale. A famous void can hold the imagination because it appears to offer a ready-made stage for disappearance. It is large, dark by comparison with its surroundings, and widely repeated in popular descriptions of cosmic emptiness. Yet the mystery of 100,000 vanished stars does not belong there. The language of the headline invites a connection, but the scientific setting lies elsewhere. The problem is not one of galaxies missing from a giant underdense region of intergalactic space. It is a problem tied to how stars are identified, counted, and compared in places much closer and far more structured. A star count is a local kind of measurement by astronomical standards. It depends on surveys that can distinguish one source of light from another, measure brightness, sometimes track motion, and decide whether a faint point is truly a star or something else. That kind of work happens within nearby galaxies or in the regions around them, not across a void hundreds of millions of light-years away. At the distance of the Boötes Void, ordinary stars in most galaxies cannot be tallied one by one through broad sky surveys. Astronomers there work with galaxies as the main visible units. A missing population of stars, by contrast, becomes meaningful only where observational detail reaches down to the stellar level. This is why the apparent mystery shifts inward from cosmic architecture to observational environment. A report about vanishing stars usually grows out of a comparison between expected and detected objects in a catalogue. It may involve a region of sky where stars should appear according to one model, one survey, or one earlier count, but where a later analysis finds fewer sources than anticipated. Such a discrepancy does not require a large physical emptiness like a void. It requires a field of observation in which stars are individually relevant, and in which methods of detection, classification, and filtering matter. The difference between these two settings is not small. In one case, astronomers ask how matter is distributed over vast distances and why some volumes contain far fewer galaxies than others. In the other, they ask whether a specific stellar population is present, missing, hidden, or misidentified within a much closer and more detailed environment. The first question belongs to cosmology, the study of the universe on its larger scales. The second belongs more to galactic astronomy and survey science, where the behavior of instruments and the structure of nearby systems shape the answer. Headlines often flatten this distinction because both situations can be described with the language of absence. A void is a kind of absence, though only relative. A shortfall in star counts is another kind of absence, though often only apparent. Once both ideas are put into ordinary language, they begin to sound as though they belong to the same mystery. But scientific accuracy depends on resisting that flattening. One absence refers to the sparse placement of galaxies across immense space. The other refers to a mismatch between expected and observed stars in a region where stars can actually be counted. In a proper stellar setting, the sky is not an empty volume but a crowded projection of sources layered across distance. Foreground stars from the Milky Way may overlap with background systems, dust may dim some objects, bright stars may wash out faint neighbours. Repeated observations may measure slightly different properties depending on instrument sensitivity and observing conditions. A survey may apply selection rules, keeping some sources and rejecting others. A faint star may enter one catalogue and fail to enter the next, not because it has ceased to exist, but because the threshold for reliable detection has changed. The classification method has shifted, or the source falls into an ambiguous range between categories. The phrase vanish stars therefore demands caution. In astronomy, disappearance from a list is not identical to disappearance from the sky. A catalogue is a constructed record. It reflects physical reality, but it also reflects choices in data processing, definitions of confidence, handling of noise, correction for crowding, and the treatment of uncertain measurements. When a large number of stars appears to go missing, one of the first tasks is to determine whether the absence is physical or procedural. The answer often lies not in a dramatic cosmic event, but in the transition from one observational framework to another. This makes the true environment of the mystery more modest in scale, but richer in detail. It is likely to involve nearby galactic structure, perhaps the outer regions of a galaxy, a faint companion system, a stellar stream, or a sparse halo population. These are places where stars are real individual entries in a scientific census. They are also places where incompleteness becomes serious. A dense inner region can confuse sources through overlap, while a thin outer region can lose them because they are too faint and too spread out. In both cases, the counting problem emerges from the interaction between real stellar populations and the limitations of observation. The correction away from the Boötes Void also restores the timeline of the problem. A cosmological void forms over immense spans of time through the slow flow of matter toward denser structures. That process is gradual and statistical. A mismatch in stellar counts may arise much more abruptly in the history of observation, when a new survey replaces an old one, when improved motion measurements reclassify objects, or when a better model of contamination alters the estimated number of true stars in a sample. The physical stars themselves may not have changed at all. What changes is the map drawn by astronomers. This does not mean every case of apparent disappearance is an error. Some stars do vary strongly in brightness. Some explode. Some collapse into compact remnants that emit little or no visible light. Some are stripped from one structure and dispersed into another, becoming hard to trace as members of the original population. But even these real processes must be studied in settings where stars are observed as stars, not in a celebrated void whose fame comes from the sparse count of galaxies. Observations indicate that many astronomical mysteries become clearer once the correct scale is chosen. The same is true here. The Boötes Void remains an important and fascinating part of the cosmic web, but it does not provide the proper physical stage for a claim about 100,000 vanished stars. That mystery, whatever form it truly takes, belongs to a nearer and more textured realm of astronomy, where stellar populations can be surveyed, where records can conflict, and where absence must be measured against method as carefully as against nature. The dramatic frame of a giant void falls away, and in its place appears a quieter but more exact scene, not cosmic emptiness, but the difficult work of deciding what the sky really contains. Stars do not occupy the universe as scattered points without belonging. They live inside galaxies, and a galaxy is less like a cloud than a gravitational city, vast and ordered by mass, motion, and time, to move inward from the broader setting of voids and large-scale structure. The mind now settles on the galaxy itself, because this is the true environment in which any large count of stars must be understood. A galaxy gathers stars, gas, dust, and dark matter into a single system held together by gravity. Within it, stars are born, age, move through different orbits, and sometimes die. If many stars seem to be missing, the first proper question is not what has happened to space between galaxies, but what it means to count stellar residents inside these immense and varied homes. Galaxies come in several broad forms. Some are spirals, with flattened disks, central bulges, and winding arms rich in gas and younger stars. Some are elliptical, smoother in appearance, shaped more like rounded swarms of older stars with less cold gas available for new star formation. Others are irregular, lacking a simple shape, often shaped by interaction or small size. These differences matter because the number, brightness, and distribution of stars depends strongly on the type of galaxy being observed. A spiral disk may contain bright young stars along its arms, while an old elliptical may hold great numbers of dimmer ancient stars spread through a more uniform body. A small irregular galaxy may show patchy star formation in one region and little in another. Even before counting begins, the nature of the host system sets the conditions. The visible form of a galaxy is only part of its structure. Around and through the luminous parts lies a larger dark matter halo, invisible to telescopes in ordinary light but inferred from the motions of stars and gas. This halo extends well beyond the bright regions and provides much of the galaxy's gravitational framework. Within that framework, stars move on orbits determined by the overall mass of the system. Some travel in orderly disk paths, circling the center in a common direction. Others move through more scattered three-dimensional paths in bulges and halos. Their motions preserve a long record of how the galaxy formed and how it interacted with neighbors over time. A galaxy is therefore not merely a container for stars, it is a historical system. Some of its stars form within its own gas clouds. Others are acquired when smaller galaxies merge into it, or are torn apart by tidal forces, which are differences in gravity across an extended object. Over billions of years, a galaxy can grow by swallowing companions, stretching their stars into streams, mixing populations of different ages and chemical compositions. This means that a star count is never just a number, it is also evidence of assembly, collision, migration, and survival. A missing population may reflect not disappearance, but the difficulty of tracing stars that have changed location or lost the shape of their original grouping. The scale within a galaxy is also more intimate by astronomical standards. Distances are still enormous, but they are small enough that stars in nearby galaxies or within the Milky Way can be studied individually. This is the key difference from the outer regions already left behind. A galaxy allows the individual star to become a unit of observation. Its brightness can be measured, its colour can be estimated, its motion across the sky can sometimes be tracked, its spectrum, which is the spread of its light into component wavelengths, can reveal temperature, composition, and movement toward or away from the observer. Once stars are observed this way, the possibility of counting them becomes real, but so does the possibility of misunderstanding the count. No galaxy presents all its stars equally. The brightest stars are easy to detect even at considerable distance, but they are only a small fraction of the whole population. Most stars are relatively dim. Many red dwarfs, for example, shine weakly and can vanish beneath the detection threshold of a survey if they are too far away or obscured by dust. Even in a nearby galaxy, the visible sample is biased toward brighter members unless observations are deep enough to reach the faint end of the population. This creates a basic challenge. Astronomers rarely count every star directly. They often count a subset and infer the larger population through models and statistical methods. Crowding creates another difficulty. In dense regions near galactic centers or within rich clusters, many stars may lie so close together in the sky that their light blends. A telescope then records a brighter patch rather than distinct points. More powerful instruments and careful data analysis can separate some of these blended sources, but not perfectly in every case. In sparse outer regions, the opposite problem appears. Stars may be so faint and so far apart that the survey misses them individually, especially against background noise. Thus both density and thinness can distort the census, each in a different way. Galaxies also contain matter that affects the passage of light. Dust grains mixed with gas absorb and scatter light, especially at shorter wavelengths. This can dim stars, redden their appearance, and hide whole regions from optical view. Infrared observations can look through some of this obscuration, but not under all conditions or with equal resolution. A star hidden by dust has not vanished. Yet in a visible light survey it may effectively drop from the count. If enough stars occupy dusty regions, the shortfall can become large without implying any physical loss of stars from the galaxy. The idea of 100,000 missing stars sounds dramatic, mainly because the human mind imagines stars as singular objects, each stable and obvious. A galaxy changes that sense of scale. Large galaxies contain hundreds of billions of stars. Even smaller systems can contain millions. Within such populations, a number like 100,000 may be either very large or relatively modest, depending on the context. In a compact star cluster, it may represent nearly the whole system. In a major galaxy, it may be a tiny fraction of the total. The scientific meaning depends entirely on where the stars should be, how they were counted, and what kind of population they belong to. This is why galaxies can be called star cities without distortion. Like cities, they have centres and outskirts, old districts and newer activity, crowded zones and quiet margins. They are shaped by growth, disturbance, and long memory. Their residents do not stay arranged in a simple pattern, and their census is never a casual task. To say that stars are missing from such a place is to say something that touches not only on physical reality, but also on the methods used to map that reality. The galaxy is the scale where the mystery gains proper meaning, because here stars become countable individuals within a structured home. Observations indicate that galaxies evolve through both internal processes and repeated interaction with their surroundings. It remains uncertain in many cases exactly how much of a present-day stellar population formed inside a given galaxy, and how much arrived from smaller companions over time. Yet there is broad agreement on the central point needed here. Stars are not free-floating elements of cosmic emptiness. They are members of galaxies, and any serious claim about their absence must begin with the nature of those galactic homes. Only from within that framework can a loss, a concealment, or a miscount be distinguished from one another. Beyond the bright body of a large galaxy lies a region that appears calmer than the inner disk, and less sharply defined than the central bulge. This is the local galactic neighbourhood in the broader sense, not merely the space around a single star, but the nearby environment of the Milky Way and its closest companions. It includes small dwarf galaxies, loose clouds of gas, ancient star clusters, and long, faint streams of stars stretched across the sky. In this region, the question of missing stars becomes more subtle. The stars are still close enough, in astronomical terms, to matter as individual objects in a census, yet they're often spread thinly, dimly, and irregularly. They belong to systems that are fragile, easily disturbed, and difficult to map in full. The Milky Way does not exist alone. It is part of a small association of galaxies often called the Local Group, a gravitational gathering dominated by the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy, along with many smaller dwarf companions. Around the Milky Way itself orbit a collection of dwarf galaxies, some relatively well known, others only recently identified because they are so faint and diffuse. These dwarfs may contain from a few thousand to many millions of stars. Their stars are often old, metal-poor, and weak in brightness. In this setting, 100,000 stars can be an enormous population, enough to define the visible body of a small galaxy. A shortfall of that size here would carry a very different meaning from the same number inside a giant spiral disk. Dwarf galaxies are among the most delicate structures in the galactic neighbourhood. Their gravity is weak compared with that of the Milky Way, and as they orbit their larger host they experience tidal forces that can pull them apart. A tidal force appears when gravity acts more strongly on the near side of an object than on the far side, stretching it over time. For a dwarf galaxy, repeated passages around the Milky Way can remove stars from its edges, lengthen its shape, and eventually transform it into a stream or cloud of debris. The stars are not destroyed, they are redistributed, yet once dispersed, they become far harder to recognize as members of the original system. This is one of the central difficulties of the nearby galactic environment. Stars do not remain in neat, isolated groups simply because they form together. Over long times, gravity rearranges them. A compact dwarf can become a diffuse remnant. A star cluster can lose members into the surrounding halo. A stream can wrap around the galaxy, crossing the sky in a path so wide and faint that only careful surveys can reveal it. When astronomers look for a predicted population, they may find that some of its stars are no longer where simpler models place them. The apparent absence then reflects a mismatch between expectation and the true dynamical history of the system. The nearby environment also includes stellar streams, elongated trails of stars that were once part of dwarf galaxies or globular clusters before being stretched by gravity. These streams are especially important because they show that the Milky Way continues to grow by absorbing smaller systems. Some streams are prominent enough to trace over large arcs of the sky, others are faint and fragmentary, visible only through sophisticated statistical techniques that search for groups of stars sharing similar motion and chemical composition. In a region dominated by such fragile structures, stars can easily seem to vanish from one category and reappear in another. A star once assigned to a bound dwarf galaxy may later be recognized as part of an unbound stream. The object has not changed in itself. The interpretation of its membership has changed. Another challenge lies in foreground contamination. When astronomers study a nearby dwarf galaxy or halo structure, they must look through the dense foreground of the Milky Way's own stars. The line of sight can contain large numbers of unrelated stars much closer to Earth, overlapping the target region in the sky. Distinguishing true members from foreground intruders requires more than position alone. Brightness, color, motion across the sky. And sometimes chemical fingerprints must be combined to estimate which stars belong together. Even then, uncertainty remains. A population may look richer or poorer, depending on how strictly those membership rules are applied. This makes the local galactic neighborhood a place where the idea of vanishing can arise naturally from method. Suppose a dwarf galaxy is first identified through a rough overdensity, a slight excess of stars in one patch of sky. Early estimates may suggest a certain number of members. Later, with improved data, astronomers might discover that many of those candidate stars actually belong to the foreground of the Milky Way. The apparent galaxy then shrinks. In another case, better motion measurements may reveal that genuine members are spread across a wider area than first assumed, making the original core seem depleted while the full system proves more extensive. In both cases, stars appear to be missing only because the first map is incomplete or partly mistaken. The local galactic neighborhood is also where some of the faintest known galaxies are found. A number of dwarf companions discovered in recent decades are so dim that they verge on the limit of detectability. They may contain only a few bright red giant stars visible in shallower surveys, with the rest of their populations inferred statistically. Their stars can be ancient relics from the early universe, preserved in small numbers and low metallicity. Metallicity here means the abundance of elements heavier than hydrogen and helium, which astronomers use as a clue to stellar history. Because such galaxies are sparse and faint, a shift in the depth or quality of a survey can change their apparent population sharply. What looks like disappearance may instead be the edge of observational reach. Globular clusters, though different from dwarf galaxies, add another layer to this nearby environment. They are dense spherical swarms of old stars orbiting the Milky Way, and some are known to lose stars gradually through tidal stripping. Tails of escaping stars can extend away from them, blending into the surrounding halo. Again, the story is not one of destruction but of dispersal. The stars remain, but their collective identity weakens as they mix into the larger environment. If only the core is counted, the outer lost members may seem absent. If the tails are included, the population changes again. Observations indicate that the Milky Way's neighborhood is dynamic rather than static, with small systems continually shaped by gravitational encounters and long orbital evolution. It remains uncertain in many cases exactly how much stellar material has been removed from individual dwarf galaxies and clusters over time, because the faint outer parts of these systems are difficult to trace completely. Yet the broad picture is clear. Nearby space is full of partial structures, disrupted remnants, and overlapping populations. It is a region where stars may seem to vanish not because they pass into nothingness, but because their old boundaries dissolve. In this local setting, the mystery narrows further. The problem is no longer cosmic emptiness or even the galaxy in general, but the fragile outskirts and companions where counting depends on subtle distinctions of membership and structure. Here, absence becomes delicate. A star can belong, then seem not to belong, then return to the census under a different interpretation. The nearby galactic neighbourhood holds exactly the kind of complexity in which a large number of stars can appear to go missing while the sky itself remains full. Past the nearby companions and broken outskirts of the Milky Way lies a region even thinner and more elusive, the outer halo. It is not a sharply bounded shell, but a vast, sparse domain surrounding the brighter body of the galaxy. Here the density of stars falls greatly. The disk, with its lanes of gas and frequent stars, has long since faded from view. The central bulge no longer dominates. Instead, the outer halo stretches through darkness with only scattered stellar inhabitants, ancient clusters, diffuse streams, and the hidden mass of dark matter shaping the whole region. This is a natural place for a mystery of missing stars to deepen, because the stars of the halo are few, faint, and widely spaced, and because the outer halo preserves the scars of the Milky Way's long history of growth through capture and disruption. The stellar halo as a whole contains only a small fraction of the Milky Way's stars. Most of the galaxy's stars belong to the disk and bulge. The halo is different in character. Its stars are generally old, often low in heavy elements, and travel on elongated or tilted orbits that do not line up with the orderly rotation of the disk. Many of them are thought to have arrived from smaller galaxies that fell into the Milky Way long ago and were gradually torn apart. In this way, the halo is not only a region of low density, it is also a record of assembly. Each scattered population may preserve the memory of some earlier merger, though that memory often survives only in faint motions and subtle chemical patterns. In the outer halo, the problem of counting is shaped first by distance. A star that is already dim by nature becomes difficult to detect when placed tens or even hundreds of thousands of light-years from Earth. Bright giant stars can still be seen at great ranges, but they are rare. Most stars are much fainter, and many drop below survey limits. This means that a stellar population in the halo is often traced through only its brighter representatives, while the much larger number of faint stars remains inferred rather than directly counted. When astronomers estimate the size of such a population, they rely on models of how many faint stars should accompany the visible bright ones. If the visible sample is incomplete or contaminated, the estimate can shift greatly. The outer halo is also difficult because it is not visually obvious. A spiral arm can be photographed as a luminous structure. A star-forming cloud can stand out through emission or dust. The outer halo usually does neither. It reveals itself through patient surveys that search for tiny overdensities of stars, for coherent streams moving together, or for unusual distributions of colour and brightness against the broader background. A small group may emerge statistically before it appears convincing to the eye. This makes the region scientifically rich, but visually deceptive. It does not announce its populations clearly. It requires interpretation. Within this environment, 100,000 stars is both many and very little. It is many because the halo is sparse, and such a number can represent a meaningful structure such as a faint dwarf remnant or a long disrupted stream. It is very little because the Milky Way itself contains hundreds of billions of stars. This duality matters. A headline can make the number sound absolute and overwhelming, but in the outer halo the significance depends on concentration, identity, and expectation. 100,000 stars gathered into a small visible system would be notable. The same number spread thinly along a long arc of sky could become nearly invisible as a collective object, even though the stars remain present. The stars of the outer halo are often ancient, formed early in cosmic history, when the chemical composition of the universe was simpler. Astronomers describe such stars as metal poor, meaning they contain relatively low amounts of elements heavier than hydrogen and helium. This chemical simplicity makes them valuable for studying the early history of star formation and galactic growth. It also means that many halo populations are linked to old systems that have survived for long times, or to remnants of systems that were broken apart billions of years ago. A missing population in this region may therefore reflect not a recent event, but the cumulative effects of ancient disruption combined with modern observational limits. The shape of the outer halo is not smooth. It contains shells, streams, clouds, and clumps, all signs that the Milky Way has not grown quietly. Some of these structures are clearly identified, others remain tentative because the available data are too thin. A patch of sky may show a weak excess of stars that suggests a new stream or remnant dwarf galaxy. Later analysis may strengthen that case, weaken it, or reinterpret the same stars as part of some already known structure. In a region this faint, boundaries are uncertain. One structure can overlap another. A few candidate stars can determine whether a feature looks real or accidental. A change in classification can therefore make an entire population appear to shrink or vanish. Motion becomes especially important here. Modern surveys can measure how stars move across the sky, though the precision decreases for more distant and fainter objects. When motions are known, astronomers can separate some halo stars from foreground disk stars and can identify groups that travel together. But motion data also introduce thresholds. A star with uncertain motion may be excluded from a clean sample even if it truly belongs. A stricter catalogue may produce a purer list but a smaller one. This is a recurring pattern in astronomy. Better data do not always increase the number of accepted objects. Sometimes they reduce it by removing doubtful cases. What disappears from the sample may be uncertainty rather than stars. The outer halo also lies within a region dominated gravitationally by dark matter. Though invisible, this mass shapes the orbits of halo stars and the fate of dwarf galaxies entering the Milky Way's pull. The halo stars move through a deep potential well, and their arrangement helps astronomers infer the distribution of that unseen matter. This makes each halo population doubly important. It is both a group of stars and a tracer of the galaxy's hidden mass. When a predicted population is not found where expected, the question is not only where the stars are, it is also whether the model of the system's past motion or its underlying gravitational structure needs revision. Observations indicate that the outer halo is built from many accreted fragments, meaning material acquired from smaller galaxies over long periods. It remains uncertain how complete the present map of that region truly is, especially at the faintest and most distant limits. Some structures may still await discovery, others may be less substantial than first believed. This uncertainty is not a weakness of the science, but a property of the terrain itself. The outer halo is real, ancient, and informative, yet it is observed at the edge of difficulty. In this thin frontier, Absence becomes especially easy to create through method alone. A structure may be predicted from partial evidence, then fade under stricter analysis. A population may be spread too widely to stand out. A remnant dwarf may have lost so many stars to tidal forces that only a traceable core remains, while the rest mingle with the wider halo. The stars have not entered a void. They have entered a state of near invisibility, where low brightness, large distance, and broken identity make them hard to recover. The outer halo is therefore a fitting inward step in the mystery, a region where stars are present but fragile in the record, and where a large number can seem to dissolve into the dark without any need for extraordinary physics. Within the outer halo, some of the clearest signs of the Milky Way's long and patient growth appear not as whole galaxies, but as fragments. A faint dwarf galaxy may survive only in part. A compact star cluster may loosen at the edges. A once coherent system may become a long and delicate stream. This region of faint dwarfs and broken streams is where the idea of vanish stars grows more tangible, because here the stars truly leave one visible form and enter another that is much harder to recognize. They are not erased. They are stretched, diluted, and mixed into the larger body of the halo until the old system becomes difficult to define. A dwarf galaxy is a small galaxy in both mass and brightness, when compared with a large spiral such as the Milky Way. Yet even a small galaxy is still a gravitational society of stars, dark matter, and in some cases gas. Some dwarf galaxies are compact and relatively easy to identify. Others are extremely diffuse, with stars spread thinly over a wide patch of sky. In the outer halo, many of the faintest known dwarfs occupy this second category. They may contain only a weak overdensity of ancient stars, barely rising above the background. Their existence becomes apparent only through careful statistical comparison between one region of sky and another. These fragile systems orbit within the stronger gravitational field of the Milky Way. Over long times, the larger galaxy pulls more strongly on the near side of the dwarf than on the far side. This differential pull produces tidal stripping, a gradual removal of stars from the dwarf's outskirts. If the dwarf passes close enough to the Milky Way, the effect strengthens. Outer stars become unbound first. They drift away along the dwarf's orbit, forming leading and trailing extensions. With each passage, more stars may be lost. The original galaxy shrinks, and its former members begin to mark out a stream. A stellar stream is a narrow or broad trail of stars that once belonged to a single bound object. Some streams come from disrupted dwarf galaxies. Others come from globular clusters, which are dense balls of old stars. The stream preserves, for a time, the memory of a common origin. Its stars share orbital properties, and often similar chemical histories as well. But a stream is a much weaker visual structure than a compact galaxy or cluster. Its stars are separated over great distances. The density along the stream can vary. Gaps may appear where gravitational interactions disturb the flow. Parts of the stream may cross regions of sky crowded with unrelated stars. Under such conditions, the stream can fragment in the record long before it fully fragments in reality. This makes broken streams especially important to the mystery. A stream may not be missing in the physical sense. It may simply fail to appear as a single continuous object in available data. One part may be clearly detected, another may fall below the threshold of confidence, and a third may be misclassified as part of the general halo. The observer sees interruptions and may speak of absent stars, while the deeper truth is that the stars have been spread into a form that the survey struggles to follow. A once obvious population becomes a faint geometry written across the sky. The same process affects dwarf galaxies in transition. Some systems are caught between identities. They're no longer fully bound dwarfs, yet not easily mapped as streams. Their central regions still contain a recognizable concentration of stars, but their outer parts are stretched and partly detached. In such cases, the estimated population can depend strongly on where astronomers draw the boundary. A narrow boundary produces a smaller and cleaner count. A wider boundary includes more possible members, but also more contamination from unrelated foreground and background stars. The number of stars that seem to belong to the object may shift by large amounts, without any change in the sky itself. This is one reason why 100,000 stars can become a meaningful and unstable figure in the outer halo. For a faint disrupted dwarf, that number may describe the inferred total population rather than a direct count of individually confirmed members. The estimate may be built from a smaller set of visible giant stars combined with assumptions about the unseen faint majority. If later work reveals that the object is more disrupted than first thought, or more contaminated by foreground stars, or more extended across the sky, then the estimate may change. A large apparent loss can emerge simply because the original picture of the object's structure was too neat. Streams also respond to encounters with other masses. The Milky Way contains giant molecular clouds in the disk, dark matter subhalos predicted by theory, and other structures that can perturb the path of a stream. These encounters can puff up the stream, create density variations, or shift stars slightly from the main path. Observations indicate that some streams show gaps and irregularities, though it remains uncertain in particular cases whether these come from dark matter clumps, ordinary gravitational encounters, or limitations in the data. What matters here is the consequence for visibility. A disturbed stream is harder to detect as a coherent population, and parts of it may slip from notice. Chemical composition offers one path back through this confusion. Stars that form together often share similar abundances of heavy elements. Astronomers use spectroscopy, the study of light separated by wavelength, to measure these abundances when possible. In a broken stream or disrupted dwarf, chemistry can help reconnect stars that are now far apart on the sky. Motion can help as well. If stars share similar trajectories, they may reveal their common origin even after their parent system has been torn apart. But such measurements are demanding. They are easier for brighter stars than for faint ones, and the faint stars are usually the majority. Thus, the reconstruction of a broken system is often partial. The invisible bulk still has to be inferred. There is also a deeper historical reason why the outer halo is full of these remnants. Large galaxies grow hierarchically, meaning through the gradual addition of smaller systems over time. The Milky Way has done this repeatedly. Some captured dwarfs were large enough to leave major imprints. Others were small and have mostly dissolved into the background. The halo seen today is therefore not a smooth ancient layer, but a collage assembled from many disrupted arrivals. In such a collage, stars are often present without their original labels. They survive physically while disappearing structurally. Observations indicate that known streams and faint dwarf galaxies account for only part of the Milky Way's accretion history. More remnants are likely to exist in forms too diffuse or too incomplete to be easily recognized at present. It remains uncertain how many such structures are still hidden in the data, or how many stars from old mergers have already mixed beyond practical recovery. This uncertainty creates fertile ground for apparent disappearances. A population predicted from one model of disruption may fail to appear because the real debris is broader, older, fainter, or more phase mixed than expected. Phase mixing here means the gradual spreading of stars around an orbit until their original grouping becomes hard to detect. In this region, then, vanish stars are often stars that have crossed a boundary of recognizability. They have moved from dwarf to stream, from stream to fragments, from fragments to halo background. Each step preserves the stars but weakens the signal of their common origin. The eye that searches for a tidy object may conclude that much has been lost. The patient survey finds instead that gravity has been rearranging the evidence for billions of years. Faint dwarfs and broken streams do not hide a dramatic cosmic subtraction. They reveal a quieter truth, that stars can leave a visible home and remain fully real while becoming difficult to gather again into a single count. At this stage of the inward path, the region is no longer a place in space alone. It becomes a region of method. The stars remain in the outer halo, in faint dwarfs, in broken streams, and across crowded fields of view. But now the focus settles on the machinery by which astronomy turns light into a census. A sky survey is not merely a photograph. It is a systematic effort to record positions, brightness, colours, motions, and sometimes distances for vast numbers of sources across the sky. The meaning of any vanished population depends heavily on how such surveys work, what they can detect, what they reject, and how they decide that one faint point of light is truly a star. A modern survey begins with repeated imaging, often through several filters that isolate different ranges of wavelength. From these images, software identifies sources that rise above the background. Each candidate source is measured. Its location on the sky is fixed. Its brightness is estimated. Its shape is examined to decide whether it looks like a point source, which may indicate a star, or a more extended object, which may indicate a galaxy. The survey then compares repeated observations to improve confidence and reduce noise. In some projects, it also tracks how the source shifts over time. That apparent shift can reveal motion across the sky or the changing viewpoint caused by Earth's orbit. This process sounds orderly, yet every step contains thresholds. The background is never perfectly dark. Detectors contain noise. Cosmic rays strike instruments. Bright nearby stars spill light into surrounding pixels. Atmospheric turbulence affects ground-based images, while even space telescopes face instrumental limits of their own. A source must be bright enough and distinct enough to survive all of this. If it does not, it may never enter the catalogue. In this sense, a star is not counted simply because it exists. It is counted because it crosses the survey's boundary between detectable and undetectable. That boundary is especially important in sparse populations. If astronomers seek a faint dwarf galaxy or a disrupted stream in the halo, many of its stars may sit very close to the detection limit. A small difference in image depth, noise treatment, or source selection can remove a large fraction of the expected members. The stars themselves remain in the sky, but the survey may not retain them as reliable detections. This is one of the quiet ways in which apparent disappearance begins. It does not start with stars going out. It starts with the rules of admission into the record. Large sky surveys such as Gaia add another layer. Gaia does not simply image stars. It measures their positions, brightness, motion across the sky, and for many stars their distances through parallax, the slight apparent shift caused by Earth's motion around the Sun. This makes Gaia extraordinarily powerful for separating foreground stars from more distant populations. A star that seemed to belong to a faint halo structure may later prove to be a nearer Milky Way star once its motion and distance are known. As the data become more precise, membership lists can shrink. This can look like loss, but it often means improvement in the purity of the sample. The reverse can happen as well. A survey with better motion data may uncover stars that were once hidden within the general background, because their shared movement was not yet recognized. A stream that seemed broken can become more continuous. A dwarf galaxy can appear more extended. A sparse structure can gain new members and become more convincing. Survey science, therefore, does not move in one direction only. It both removes and restores. The important point is that catalogue counts are not raw facts lifted directly from nature. They are the result of a method refined over time. Colour and brightness diagrams are another essential tool. When astronomers plot stars according to these two measured properties, genuine members of a shared population often align along recognizable patterns tied to stellar evolution. Old, metal, poor stars occupy one set of tracks. Younger stars occupy others. By comparing an observed field with theoretical or empirical patterns, astronomers estimate which stars may belong to a given structure. But this too involves uncertainty. Foreground stars can imitate the expected colours of true members. Faint measurement errors can blur the pattern. A population estimate built this way is useful, but it is statistical. It can be revised sharply when better data arrive. Completeness is one of the quiet technical terms that shapes the whole mystery. Completeness describes the fraction of real sources that a survey successfully detects. Near the bright end, completeness may be high. Near the faint end, it falls. Astronomers try to measure this by injecting artificial stars into images and testing how many are recovered, or by comparing overlapping surveys of different depths. From this, they estimate how many real stars are likely being missed. If completeness is misunderstood, the inferred total population can be too large or too small. A later correction can make tens of thousands of stars seem to appear or vanish, though what has truly changed is the estimate of what the survey failed to catch. Cross-matching between catalogues introduces another source of difficulty. Astronomers often compare one survey with another, linking entries that appear to represent the same star. But positions shift over time, measurement errors differ, and crowded fields complicate the match. A source in one catalogue may fail to find a secure counterpart in another. It may be split into multiple detections, merged with a nearby source, or rejected as uncertain when many objects are involved. These small mismatches can grow into a large numerical discrepancy. What looks like a missing population may partly be the friction between two ways of recording the same sky. Selection cuts also matter. To build a clean sample, astronomers often exclude stars with uncertain motion, poor photometry, suspect shape, or conflicting measurements. This improves reliability but reduces numbers. A strict selection may discard many genuine stars along with many false ones. A looser selection may retain the stars but at the cost of greater contamination. There is no perfect balance. The apparent size of a population depends on where that balance is set. Different studies may reach different totals while looking at the same underlying region. Observations indicate that modern surveys are transforming knowledge of the Milky Way and its outskirts by providing far more precise maps than earlier generations could achieve. It remains uncertain in many faint and diffuse systems exactly where the line should be drawn between true members and background contamination. That uncertainty is not a small technical footnote. It often determines whether a structure appears rich, poor, disrupted, or even real at all. The method becomes part of the physical story because the object exists at the edge of detectability. In this inner region of the mystery, stars vanish most often inside the catalogue before they vanish anywhere else. They fall below detection limits, fail selection cuts, lose secure matches, or are removed when better motion data reveal that they never belong to the target population. The sky itself changes little on human timescales. What changes is the precision of the census. This survey does not invent the stars, but it decides which ones can be confidently named, grouped, and counted. That decision, repeated across millions or billions of sources, is powerful enough to make a population seem to fade from view without any star having physically gone away. Once a sky survey has turned light into a catalogue, another difficulty begins. Different catalogues do not always tell the same story. They may look at the same region of sky and return different numbers of stars, different estimates of distance, different motions, or different judgments about what kind of object each source is. This does not mean that one survey sees reality and another sees illusion. More often, it means that each survey reaches the sky through different instruments, different observing conditions, different depths, and different rules of interpretation. In this region of the mystery, stars seem to vanish not because they leave the sky, but because the record of the sky is never a perfect mirror. It is a layered construction, and when one construction replaces another, large discrepancies can appear. A catalogue is shaped first by the instrument that creates it. One telescope may work mainly in visible light, another in infrared. One may observe from the ground through atmosphere, another from space. One may reach faint stars well but with limited resolution, while another may separate crowded stars more effectively but survey a smaller area or a different range of brightness. These choices shape the population that enters the record. A cool dim star partly obscured by dust may appear more clearly in infrared than in visible light. A crowded field that blends in one survey may separate into distinct stars in another. A faint stream may stand out in a deep survey and nearly disappear in a shallower one. Thus disagreement can begin before any data analysis even starts. The treatment of uncertainty then adds another layer. Every source comes with measurement errors. Its brightness has a range of possible values. Its position is known within limits. Its motion may be clear or barely measurable. One team may accept sources with larger uncertainties in order to capture more possible members of a faint structure. Another may insist on stricter quality cuts, sacrificing completeness for reliability. Both approaches are defensible, but they do not produce the same census. A population may look rich under looser rules and sharply smaller under stricter ones. The stars have not changed. The confidence assigned to them has changed. Distance estimates are a particularly powerful source of disagreement. In nearby stellar work, a source may be classified as part of a halo structure or as a foreground intruder depending on how far away it seems to be. A small shift in the estimated distance can move a star from one category into another. Parallax measurements help, but they become less precise for very distant and faint stars. When direct distance is uncertain, astronomers infer it from brightness, colour, and assumptions about the kind of star being observed. If those assumptions differ, the resulting population can differ as well. A star included in one study may be excluded in another simply because its inferred distance falls on opposite sides of a membership boundary. Classification adds further instability. A faint point of light may be treated as a star in one catalogue and as a compact galaxy in another. In regions near the detection limit, shape measurements become noisy, and the distinction is not always secure. This matters greatly for halo work, where unresolved distant galaxies can mimic faint stars. If a catalogue becomes more conservative about this separation, the number of accepted stars may drop sharply. A supposed stellar overdensity may weaken or disappear. What vanishes in that moment is not physical matter but a prior interpretation. Time also matters. Surveys are often built from observations taken at different epochs, meaning different moments separated by months or years. A star that moves noticeably across the sky may line up imperfectly between datasets. Variable stars, which change brightness over time, may look secure in one survey and marginal in another. A source near a bright neighbour may be detected in one set of seeing conditions and lost in another. These small time-dependent effects complicate matching and classification. When millions of sources are involved, their collective impact can become large enough to alter the inferred size of a faint population by many thousands. There is also the problem of modelling the background. To identify a weak dwarf galaxy or diffuse stream, astronomers must estimate how many ordinary Milky Way stars and unrelated objects should appear in the same field by chance. This background model is then subtracted from the total. If the background is overestimated, the target population shrinks. If it is underestimated, the target appears richer than it truly is, in very faint systems. The signal may be only a modest excess above the background. A slight change in the model can therefore create a large relative change in the inferred number of members. In extreme cases, a claimed system may weaken to the point that its existence becomes uncertain. Statistical inference can deepen the mismatch. One study may estimate total stellar population by fitting a luminosity function, which describes how many stars should exist at each brightness. Another may estimate from the number of visible red giant stars. Another may use simulated populations matched to color and motion data. Each method carries assumptions about age, metallicity, distance, completeness, and contamination. If those assumptions differ, the resulting population size can differ as well. This is especially true for dim systems in the halo, where most stars are not directly detected and the total must be inferred from the minority that are. As data improve, older catalogues often become obsolete in detail while remaining historically important. A survey that once represented the best available map may later be revised or superseded by one with better astrometry, deeper imaging, or cleaner source classification. The transition can be unsettling because the newer result may seem to remove a substantial number of stars from a known structure. Yet from the scientific point of view, this is often progress. The apparent loss reflects the replacement of a rougher census with a sharper one. The object under study may become smaller, more extended, more fragmented, or less certain than first believed. That is not a failure of astronomy. It is the normal correction of a difficult measurement. This is why catalogue disagreement must never be mistaken automatically for cosmic disappearance. The language of vanishing is tempting, because subtraction is easy to imagine, but subtraction in astronomy often occurs first on paper and in code. A source fails a quality cut, a match is rejected, a background model rises, a distance estimate shifts, a classification changes from star to galaxy. Each action is modest. Together, they can remove a very large number of apparent members from a sample. The final result may look dramatic, but the drama lies in the complexity of inference, not in a sudden event in the heavens. Observations indicate that cross-comparison between surveys is one of the main engines of refinement in modern astronomy. It remains uncertain, for many faint halo systems, which combination of cuts, models, and classification choices best captures the true underlying population. Different teams can therefore reach somewhat different answers while using valid methods. Over time, consensus tends to improve as more precise motion data, deeper imaging, and spectroscopy reduce the ambiguity. But the path to that consensus is full of numerical shifts. In this region of the mystery, disappearance becomes an argument between maps. One catalogue says the stars are there. Another says many of them do not qualify. A third finds some in new places and rejects others entirely. The sky above remains steady, but the census moves under the pressure of better evidence. To the outside eye, 100,000 stars may seem to have gone missing. To the working astronomer, it may mean that an earlier population estimate has been cut down by improved discrimination. The loss is real inside the catalogue, but whether it is real in nature is exactly the question that must be tested with patient care. Even when surveys agree in broad outline, the sky still hides stars behind ordinary physical barriers. Light does not travel from every star to every detector in a simple and equal way. It passes through dust, across uneven backgrounds, near bright neighbours, and through observational conditions that can suppress what is faint and preserve what is strong. In this region of the mystery, stars do not vanish because a catalogue changes its rules. They vanish because the path between source and observer is imperfect. Dust, glare, and hidden light create one of the oldest and most persistent forms of astronomical absence, where real stars remain present but difficult to see. Dust in space is made of tiny solid grains mixed with gas. Though the grains are individually small, their collective effect across great distances can be substantial. They absorb and scatter light, especially at shorter wavelengths, so that stars behind dusty regions appear dimmer and redder than they truly are. This process is called extinction when the total loss of light is emphasized, and reddening when the change in color is emphasized. In either case, the effect can move a star toward the limits of detectability or change its apparent properties enough to affect classification. A star that is faint and red because of dust may be mistaken for a different kind of object, or may simply fall below the threshold of a survey built in visible light. Within the Milky Way, dust is concentrated most strongly in the disk, especially along the plane where gas clouds and star formation are common. Halo studies often try to avoid the thickest dusty regions, but they cannot escape the issue entirely. Lines of sight through the galaxy vary in their dust content, and even moderate extinction can alter the number of stars recovered from a given field. A faint dwarf galaxy or stellar stream behind a dustier patch of foreground sky may appear poorer than a similar structure seen through clearer space. If the dust correction is incomplete or uncertain, the inferred stellar population can be skewed. The stars themselves have not changed. The foreground has altered the view. Infrared observations help because longer wavelengths can pass through dust more effectively than visible light. This is why infrared surveys often reveal stars hidden in dusty regions that appear nearly opaque in ordinary optical images. Yet infrared is not a perfect solution. Resolution may differ. Background emission from warm dust can complicate detection, and extremely faint stars may still remain hard to recover. Moreover, not all surveys operate in the same wavelength range. So a population that appears substantial in one dataset may look reduced in another, simply because dust suppresses the shorter wavelength view more strongly. Glare introduces a different kind of concealment. A bright star does not only occupy its own point in an image, its light can spread outward through instrumental effects and scatter, raising the local background and making nearby faint sources harder to detect. In dense fields, this can create small zones of invisibility around bright stars, especially for objects close to the survey limit. If a diffuse stellar population lies across a field containing several bright foreground stars, parts of it may effectively disappear in the glare. This is a local effect, but repeated across a wide area it can remove many faint detections from a sample. The sky itself also shines. Airglow in Earth's atmosphere, moonlight, unresolved distant sources, and diffuse galactic light all contribute to the background against which stars must be detected. A faint source is never measured against pure darkness. It is measured against a surface of fluctuating brightness. When the background rises, the contrast falls. A star that would have been recorded on a darker night may fail to stand out on a brighter one. Space-based observatories avoid some of these problems, but they still face instrumental backgrounds and scattered light from within the telescope system. Hidden light is therefore not an occasional nuisance, it is a constant condition of observation. In studies of faint halo structures, uneven background is especially important. A stream can be broad and low in surface density, meaning that its stars are spread thinly across a large area. The signal of the structure is then only a slight excess over the ordinary background field. Dust variation, scattered light, or patches of poor image quality can lower that excess until parts of the stream no longer seem statistically significant. A once continuous structure may appear broken. A weak overdensity that suggested a dwarf galaxy may shrink. This kind of disappearance is not even individual. It happens to the collective visibility of a population. Dust can also distort distance estimates. If a star is dimmed by foreground extinction and that effect is underestimated, it may appear farther away or intrinsically weaker than it truly is. If the extinction is overestimated, the opposite can happen. Since membership in a faint system often depends partly on inferred distance, dust enters the census indirectly as well as directly. A star may be excluded not because it is unseen, but because dust has altered its measured brightness and colour enough to place it outside the expected track of the target population. There is another complication in the form of patchiness. Dust is not smoothly spread across the sky. It forms clouds, lanes, and filaments. Some parts of a survey field can therefore be clearer than others. In a broad search area, one region may reveal faint stars readily, while a neighbouring region suppresses them. If a real structure crosses both zones, it may look richer on one side and thinner on the other. This can imitate physical disruption or asymmetry. Only after careful dust mapping and correction does the underlying distribution become clearer. Even then, uncertainty remains, particularly where dust is complex on fine angular scales. Foreground stars contribute to concealment in a more subtle way as well. A field crowded with unrelated stars increases confusion and complicates source separation. In sparse halo work, the target population may consist of only a slight statistical excess above this foreground. If the foreground is strong enough, the target begins to dissolve into it. This is not dust and not glare in the strict sense, but it is another form of hidden light. The field contains too much competing information. The desired population is physically present but observationally submerged. Astronomers attempt to correct for these effects with extinction maps, image masks around bright stars, background modelling, and multi-wavelength comparisons. These methods improve the census, but none is perfect. Extinction maps have finite resolution and uncertainty. Bright star masks remove contaminated regions but also remove any genuine faint sources behind them. Background models approximate real variation but do not capture every fluctuation. A corrected field is therefore not the same as a transparent field. Some hidden stars remain hidden, and some recovered stars remain uncertain. Observations indicate that ordinary obscuration and uneven visibility account for significant incompleteness in many wide-field surveys, especially near detection limits and in regions of complex foreground structure. It remains uncertain in some faint halo systems how much of the observed asymmetry or sparsity is physical and how much comes from variable extinction, glare, or background treatment. That uncertainty is enough to change the inferred population by large amounts when the target system is already weak. In this region, the mystery becomes quieter and more physical. No exotic event is needed. Dust lies between the star and the detector. Bright sources wash over faint neighbours. Background light raises the floor beneath the signal. A stream thins into the field not because its stars have ceased to exist, but because their contrast has dropped below what present observation can cleanly recover. Absence, here, is made from ordinary matter and ordinary optics. The stars remain in place while the path to them becomes imperfect, and that imperfection is enough to make a substantial population seem to withdraw into darkness. Even if the sky were perfectly transparent and every catalogue perfectly matched, stars would still resist a simple census, because stars themselves are not simple objects. They are often treated in ordinary thought as steady lights, each one fixed in place and brightness, quietly enduring for spans far beyond human life. In reality, many stars vary, interact, erupt, dim, brighten, or hide one another. Some exist in pairs or larger groups. Some pass through brief unstable phases. Some end their lives in ways that leave little visible light behind. In this region of the mystery, the apparent loss of stars emerges not from dust or from survey disagreement, but from the natural complexity of stellar behaviour itself. A variable star is a star whose brightness changes with time. The cause may lie within the star or outside it. Some stars pulse, expanding and contracting in a regular cycle that alters their light output. Others rotate while carrying dark star spots or bright regions across their visible surface, causing the measured brightness to rise and fall. In binary systems, one star may periodically pass in front of another, creating eclipses that dim the combined light. There are also eruptive variables, where sudden releases of energy or changes in the outer layers produce irregular outbursts. In every case, the star remains present, yet its appearance in a survey depends strongly on when it is observed. This matters because most surveys do not observe every source continuously. They visit the same field at intervals. A star near the detection limit may appear in one epoch and slip below that limit in another, especially if it varies strongly. If the catalogue construction demands repeated secure detections, the star may fail to qualify. A single image may contain it, but the final record may not. A population that includes many such stars can therefore look unstable in the data. The stars themselves are not vanishing in any deep physical sense. Their light is moving above and below the threshold of notice. Binary stars complicate the census in another way. A large fraction of stars belong to pairs or higher-order systems. When two stars lie close together on the sky, a survey may record them as one source rather than two, especially at great distance or low resolution. Later, better data may split that source into separate objects. The reverse can also happen. A faint companion may be lost in the glare of a brighter primary and fail to enter the catalogue. Thus the true number of stars in a field may be greater than the number of recorded sources, and the degree of this undercount depends on the instrument, the distance to the system, and the crowding of the field. Some binaries are more dramatic still. In close systems, stars can exchange matter. Gas may flow from one star to the other, heating into a bright disk and altering the brightness and colour of the system. In rare cases, this leads to nova eruptions, sudden brightenings caused by thermonuclear burning on the surface of a dense white dwarf. Such systems can appear unexpectedly, then fade again. A survey that catches the bright phase may catalogue a source that later seems absent. A survey that misses the bright phase may fail to recognise the system's unusual nature at all. Once again, presence and absence become partly functions of timing. Massive stars introduce another form of instability. They live fast, burn their fuel quickly, and can end in supernova explosions. A supernova briefly outshines ordinary stars by an enormous factor, then fades as the expanding debris cools and spreads. After the explosion, the progenitor star is gone as a visible ordinary star. In its place may remain a neutron star, a black hole, or a faint remnant embedded in glowing gas. This is a true disappearance in one sense, but it is rare, and it does not happen in bulk to large quiet populations. It is not a plausible explanation for a mysterious loss of 100,000 stars from a faint halo system. The scale and time scale do not fit. Real stellar death exists, but it does not occur in the numbers needed to explain such a headline. There are also stars that may collapse directly into black holes with little or no bright explosion under some conditions. Observations have suggested a small number of candidates for such failed supernova, where a massive star brightens modestly or changes behavior and then effectively disappears from visible view. This remains an active area of study, and the details are still uncertain. But even if such events occur, they are expected to be uncommon. They matter greatly for the life cycle of massive stars, yet they do not provide a likely path for the sudden apparent loss of a vast ordinary stellar population. Their rarity preserves the broader conclusion that large numerical disappearances are usually observational or dynamical, not the result of many stars individually ending at once. Compact remnants contribute further complexity. White dwarfs, neutron stars, and black holes are the remains of stellar evolution. White dwarfs can be faint but detectable. Neutron stars may be seen as pulsars if their beams sweep across Earth, though many remain unseen. Black holes emit no light directly unless matter falls into them. A region that once contained luminous stars may, after billions of years, contain many compact remnants that are difficult to detect. In this long-term evolutionary sense, stars do vanish from ordinary visible surveys, yet this is a gradual transformation built into the history of every stellar population. It does not create a sharp shortfall between one modern catalogue and another unless the interpretation of the population's age or composition changes. Age itself matters greatly. A young population contains bright, massive stars that are easy to notice but short-lived. An old population contains mostly dimmer, long-lived stars, with the massive ones long gone. If astronomers misjudge the age mix of a faint system, they may misestimate how many visible stars should be present. The absence then lies not in the sky, but in the model of stellar evolution used to predict the population. A structure expected to contain many luminous stars may instead prove ancient and faint, rich in long-lived low-mass stars that evade easy detection. What seems missing is partly a consequence of expecting the wrong kind of stellar community. There is also the problem of transience in rare objects. Some stars erupt only occasionally, some young systems flare, some interacting binaries brighten unpredictably. Though these are a small fraction of any overall population, they can influence how a sparse structure is first noticed. A field may attract attention because a few unusual stars stand out. Later, when those stars settle or fade, the same field may seem less significant. The structure itself may remain, but the eye is less easily drawn to it. Observations indicate that stellar populations are mixtures of steady and unsteady behavior, single and multiple systems, bright short-lived stars and dim long-lived ones, all evolving on different timescales. It remains uncertain in some faint halo populations exactly how much variability and unresolved multiplicity affect the inferred star count. especially near survey limits where small changes in brightness alter detectability. That uncertainty is enough to matter when the goal is to identify a very weak overdensity against a noisy background. In this region, stars refuse to behave like fixed beads on a static map. They pulse, eclipse, merge in the image, hide companions, flare, die, and leave remnants that scarcely shine. This census is therefore never only a count of what exists. It is a count of what exists in a form visible to a given method at a given time. A vanished star may be an eclipsed star, a blended pair, a faded variable, a compact remnant, or simply a member of an old dim population expected to glow more strongly than it does. The heavens remain full, yet the forms of visibility keep changing, and in those changes the illusion of disappearance grows deeper. Past the behavior of individual stars lies the larger and quieter force that reshapes whole populations over immense spans of time. This is gravity's slow rearrangement. It does not make stars disappear in the dramatic sense suggested by a headline. It moves them, stretches them, unbinds them from old structures, and blends them into broader ones. In this region of the mystery, absence is created not by destruction, and not by error alone, but by motion. A star can cease to belong to the place where astronomers first expect it, while remaining entirely present somewhere else in the same galactic system. When enough stars undergo this process, a population can seem to thin, scatter, or dissolve. Gravity acts between all masses, but in astronomy its most important effects often emerge through accumulation. A single passage near a larger body may disturb a small system only modestly. Repeated passages over billions of years can transform it completely. A dwarf galaxy orbiting the Milky Way does not keep its stars forever. Outer members are the first to feel the difference between the dwarf's own weak pull and the stronger pull of the larger galaxy. As those stars drift outward, the dwarf becomes smaller, dimmer, and less sharply defined. The missing stars have not gone far in cosmic terms, yet they no longer reinforce the visible concentration that first identified the object. This process can be described as tidal evolution. The word tide is used because the underlying physics resembles, in a general way, the difference in gravitational pull that raises tides on Earth. In a galactic context, the difference acts across a whole star cluster or dwarf galaxy. The near side and far side do not feel exactly the same force. Over time the system stretches. Stars escape along preferred directions, often roughly aligned with the orbit. Once loose, they do not stop existing as a related population at once. They continue moving through space with similar energies and paths, marking out a stream or envelope, but the denser center has lost them, and that loss alters the count. Even within the Milky Way itself, gravity rearranges stars continuously. Stars in the disk migrate somewhat from their birthplaces. Halo stars follow long orbits that carry them through different regions of the galaxy. Globular clusters lose outer members gradually. Dwarf remnants continue to shed stars long after the first dramatic phases of disruption are over. A present-day map is therefore never a map of fixed residence. It is a momentary view of a system in motion. If astronomers compare that view with a simpler expectation that assumes cleaner boundaries and more stable membership, the difference may appear as unexplained absence. Mergers deepen this effect. When a smaller galaxy merges with a larger one, the process does not simply add one intact body to another. It stirs, heats, and redistributes stars through violent relaxation, a term for the rapid rearrangement of orbits during a changing gravitational potential. After such an event, stars from the smaller galaxy may end up spread over a large volume. Some retain recognizable coherence for long periods in streams and shells. Others phase, mix into the wider halo, gradually losing the clear signature of their common origin. In practical terms, this means the stars remain inside the galaxy while leaving the count of any identifiable substructure. Phase mixing is especially important because it turns obvious debris into subtle background. At first, a disrupted system may produce a narrow stream or a clear clump. As time passes, differences in orbital period cause stars to spread along the orbit. The feature becomes longer, thinner, and lower in contrast. Eventually, it can become so diffuse that the original grouping is no longer easy to recover. The stars still move within the Milky Way, still respond to the same gravitational field, and still preserve some trace of common ancestry in motion or chemistry. Yet visually and statistically, they're no longer a compact population. They have passed from object to field. This transformation creates one of the most important scientific distinctions in the entire mystery. A population can be physically conserved while observationally lost. Conservation means the stars still exist. Observational loss means they no longer stand out as a bound or even coherent structure in current data. A dwarf galaxy may once have contained enough concentration to be recognized with modest methods. After prolonged stripping and mixing, many of those same stars may belong to no easily visible object at all. A headline may say they vanished. Gravity says they were redistributed. The Milky Way's dark matter halo influences this rearrangement at every step. Though unseen, it provides much of the total gravitational potential through which stars and satellite galaxies move. Its shape affects orbits. Its substructure may perturb streams. Its depth determines how tightly stars remain bound to the galaxy, even after they become unbound from smaller systems. This means that a star lost from a dwarf galaxy is not usually lost to intergalactic space. More often, it becomes more deeply a star of the Milky Way itself, absorbed into the larger system while ceasing to reinforce the smaller one. The star has changed context, not existence. Encounters between satellites can contribute as well. Two small systems may pass near one another, exchanging energy or stirring outer stars. A globular cluster crossing the disk may feel shocks from the rapidly changing gravitational field. Even giant molecular clouds inside the Milky Way can perturb some orbits. These influences are generally modest compared with the pull of the galaxy as a whole, but over long times they matter. They roughen clean models, blur expected boundaries, and help explain why real stellar debris often looks messier than idealized predictions. There is also a matter of timescale. Gravity works slowly at galactic distances. Human language tends to favor sudden verbs such as vanished, erased, or lost. Galactic reality favors long transformations. A structure may spend hundreds of millions or billions of years changing from bound system to stream, from stream to diffuse halo component. At no single moment do all the stars depart together. Instead, the contrast of the system fades. The count within the visible core declines. The outer parts lengthen and thin. What disappears first is not the stars but the clarity of the pattern. Astronomers use simulations to understand this process. By modelling the orbit of a dwarf galaxy or cluster within a galactic potential, they can predict how stripping should unfold and where debris may travel. These simulations often reproduce the broad forms of observed streams and remnant systems, yet it remains uncertain in many individual cases exactly how much mass has been lost, how wide the debris has become, and how much of it lies below present detection limits. That uncertainty matters because a model may suggest that many stars should now occupy a broad low-contrast region that surveys struggle to recover. The stars are expected. but their present arrangement makes them hard to see. Observations indicate that the Milky Way is built in significant part through this gradual incorporation of smaller systems, and that many halo stars are the products of past accretion and disruption. It remains uncertain how much ancient debris has already become too phase mixed to identify cleanly as separate remnants. This uncertainty means that some apparent stellar shortfalls may reflect the final stage of gravitational rearrangement, where the stars have not been destroyed and not even truly hidden by dust or method alone, but blended into the larger history of the galaxy. In this region, gravity becomes the quiet author of disappearance. It does not remove stars from reality. It removes them from simple categories. A bound dwarf loses them to a stream loses them to the halo. A compact identity becomes an extended memory. The eye that seeks a stable object sees depletion and speaks of loss. The deeper view sees motion, dispersal, and assimilation into a larger whole. Under gravity's steady hand, 100,000 stars can cease to occupy the place where expectation wants them, while remaining fully present in the galaxy that has been rearranging them all along. There are cases in astronomy where a star truly does leave ordinary view. These cases are real, measured, and important, but they belong to a narrow part of stellar life rather than to the broad disappearance suggested by a large missing population. In this region of the mystery, the inward path reaches the rare endings of stars themselves. Here the question becomes more exact. Under what conditions can a star genuinely vanish from visible sight, and how often does that happen? The answer is calm and limited. Stars can end, collapse, explode, fade into remnants, or in unusual cases fail to produce the bright finale once expected. Yet these processes are individually uncommon on human timescales, and they do not provide an ordinary explanation for the apparent absence of 100,000 stars from a faint galactic structure. The life of a star depends mainly on its mass. Small stars burn their fuel slowly and can shine for spans far longer than the current age of the universe. Medium-mass stars like the Sun pass through predictable stages, swelling into red giants and later shedding outer layers before ending as white dwarfs. Massive stars live much more quickly. They exhaust their nuclear fuel in millions rather than billions of years, build heavier elements in their cores, and eventually reach a point where pressure can no longer support the inner regions against gravity. What follows may be a supernova explosion, or under some conditions a quieter collapse into a compact remnant. A supernova is one of the clearest examples of a star truly disappearing in its ordinary form. For a brief time, the explosion can outshine the entire host galaxy in visible light. Then the brightness fades over weeks and months as the ejected matter expands and cools. The original star is gone. In its place remains a neutron star, a black hole, or expanding debris enriched with heavy elements forged in the star and in the explosion itself. This is a real ending, not an observational illusion. Yet supernovae are rare. Even in a large galaxy, they occur infrequently on human timescales. Their numbers are far too small to erase vast populations of ordinary stars from a catalogue. There are also thermonuclear supernovae, in which a white dwarf in a binary system accumulates matter until runaway fusion destroys it. These events are important in cosmology because of their brightness and relative uniformity. They also represent a genuine disappearance of a star in one sense, but again the rate is low and the conditions are specific. Such events help measure the scale of the universe. They do not empty halo structures of large stellar populations. A more subtle possibility is direct collapse. In some theoretical and observational studies, very massive stars may collapse into black holes without producing a bright classic supernova. The evidence for this comes in part from a small number of candidate stars that appear to fade or vanish without the explosive display once anticipated. Observations indicate that such events may occur in nature, though it remains uncertain how common they are and under which stellar conditions they proceed quietly rather than explosively. Even if direct collapse is confirmed as a significant channel for some massive stars, it would still remain a rare fate confined to a special subset of the stellar population. It cannot plausibly account for a headline-scale disappearance of 100,000 stars in an old diffuse halo environment, where most stars are low mass and ancient. White dwarfs present another kind of disappearance, though one stretched over long time. A star like the Sun eventually becomes a compact remnant with no fusion in its core. At first it can remain hot and visible, but it slowly cools and dims. Over immense periods it will become colder still, though the universe is not yet old enough for the coldest final stage to exist naturally. Neutron stars and black holes can be harder to detect from the beginning, especially when isolated. In this sense, stellar evolution gradually transfers luminous stars into a population of much fainter remnants. But this is not a sudden subtraction from a catalogue of contemporaneous stars. It is part of the long aging of any stellar system. It changes the ratio of bright to faint objects over billions of years rather than producing abrupt modern disappearances. The age of a population is therefore crucial. A faint halo dwarf or stellar stream is usually dominated by old stars. The most massive luminous stars died long ago. What remains are long-lived low-mass stars, red giants in temporary advanced stages, and the remnants of earlier generations. This means that the rare dramatic endings of stars are not only infrequent in general, they are even less relevant in old systems where the stars most likely to explode have already completed their lives in the distant past. If a modern survey finds fewer stars than expected in such a structure, the cause is unlikely to be ongoing stellar death. It is more likely to lie in detectability, classification, dispersal, or modelling. There are other genuine ways a star can leave ordinary view. A star in a binary may merge with its companion, producing a single object and reducing the number of visible stars by 1. A star may be swallowed in an extreme interaction with a compact object. An eruptive event may alter a system so strongly that its previous identity disappears. Yet these are rare channels, each affecting small numbers of objects. Astronomy knows of them and studies them carefully, but they do not operate on the scale suggested by a large census discrepancy in a diffuse stellar population. One reason headlines drift toward dramatic endings is that true stellar death is vivid and memorable. It provides an event, a moment, and an image of finality. Surveying completeness, tidal dispersal, or background modelling do not offer the same immediate picture. Yet the quiet explanations are often the stronger ones. A population can seem absent without any need for stars to be physically destroyed. Rare real endings remain important because they define the limits of what nature can do, and because they remind the observer that not all disappearance is illusion, but they also show, by their rarity, why caution is necessary. The universe does permit true vanishing from visible light. It simply does not do so in bulk under ordinary circumstances. This distinction between possibility and plausibility matters deeply. It is possible for a star to collapse, explode, merge, or fade into a remnant. It is not plausible that 100,000 stars in an old halo-related population would all be removed from visibility through such endings on the timescales relevant to modern observation. The observed properties of those environments do not support that scenario. Their stars are too old, too low in mass on average, and too dispersed. Their apparent losses point elsewhere. Observations indicate that stellar evolution theory and recorded transients strongly support the existence of genuine stellar endings, including supernovae, compact remnant formation, and likely some cases of faint or failed explosive death. It remains uncertain in some details how often the quietest collapse channels occur, and how many such events current surveys miss. Yet these uncertainties do not change the larger conclusion. Real stellar disappearance exists, but it is uncommon and population-specific. It is not the default explanation for a broad numerical mystery. In this region, the inward path reaches the limit of literal absence. A star can truly cease to shine as an ordinary star. It can leave behind a remnant that contributes little or no visible light. It can depart from the census of the luminous sky in a physical way. But that truth is narrow, not sweeping. It belongs to rare endings, singular histories, and long evolution. When set against the much larger puzzle of 100,000 missing stars, it serves mainly as a boundary marker. It shows what real disappearance looks like, and by doing so, it reveals how unlikely it is to explain the wider mystery on its own. By this point, the mystery has passed through many layers of correction. It has moved away from a famous cosmic void, through galaxies and local companions, into the outer halo, through broken streams and survey methods, past dust and variable stars, and into the slow rearrangement caused by gravity and the rare true endings of stellar life. Now the remaining task is to examine the number itself. 100,000 sounds exact in ordinary language. But in astronomy such a number may describe very different things depending on context. It may refer to a direct count of detected stars, to an inferred total population, to a discrepancy between two catalogues, to a shortfall relative to a model, or to a population once assigned to one structure and later redistributed among others. In this region of the mystery, the number becomes evidence rather than spectacle. A number in astronomy is almost never bare. It comes with assumptions, limits, and definitions. If astronomers say that a system contains 100,000 stars, they usually do not mean that each one has been individually confirmed and listed by name. In a faint halo structure, only the brighter members may be directly visible. The rest are estimated from models of stellar populations, completeness corrections, and statistical membership. A number of this kind is not fictional. It is grounded in observation, yet it is not the same as a row-by-row inventory. If later analysis changes the assumed distance, age, contamination level, or surface extent of the system, the estimated total can shift substantially. The stars have not been recounted one by one. The inference has been revised. This matters because the meaning of missing depends on what was originally claimed. If 100,000 refers to an estimated population in a disrupted dwarf galaxy, then a later finding of fewer secure members does not necessarily imply that those stars have vanished physically. It may mean that the first estimate rested on an over-optimistic understanding of the system's size or coherence. If the number refers instead to stars expected in a certain brightness range, then a shortfall may arise from completeness limits or from a mistaken assumption about age and metallicity. If it refers to stars that should appear in one catalogue but not another, then the issue may lie in cross-matching, motion cuts, or source classification. The same number can therefore describe several different layers of absence. There is also the question of proportion. 100,000 stars in the Milky Way as a whole is a minute fraction of the total population. It would be negligible in terms of the galaxy's overall mass and light. But 100,000 stars in a small faint dwarf galaxy may represent a major share of the entire system. In a stellar stream, it may mark the difference between a clearly visible feature and one that blends into the background. Scientific importance is not measured by the emotional weight of the number alone. It depends on the scale of the system under discussion. A large-sounding number can be cosmically modest, while a modest-sounding number can be structurally decisive. This is why astronomers pay close attention to what the number is being compared with. A report may say that 100,000 stars are missing, but missing from what baseline? From a simulation, from an earlier catalogue, from a theoretical luminosity function, from the expected population of a bound remnant before tidal stripping, from the visible portion of a stream after accounting for background subtraction. Each baseline carries its own uncertainty. A discrepancy between observation and a model is not the same as a discrepancy between two direct observations, nor is either one the same as a physical destruction of stars. The word missing compresses all of these possibilities into a single dramatic term, but the scientific meaning lies in the comparison. The role of uncertainty is especially important here. A precise-sounding number can still carry a broad margin of error. In faint systems, the uncertainty in membership, completeness, and contamination can be large enough that the true population might plausibly sit well above or below the nominal estimate. Astronomers express this through error ranges, confidence intervals, and probabilistic modelling. Public retellings often strip those away, leaving only the central figure. Once the uncertainty disappears from the language, the number begins to feel harder and more mysterious than the science actually supports. The result is a sharper story and a blurrier truth. At the same time, a numerical discrepancy should not be dismissed merely because it may have an ordinary explanation. Large mismatches between expectation and observation are often valuable. They force astronomers to recheck assumptions, improve catalogues, refine models of disruption, and reconsider how faint structures are detected. A shortage of stars in a predicted remnant may reveal that tidal stripping has been more efficient than expected. It may suggest that debris has spread over a wider area. It may indicate that the background model is too simple, or that survey completeness falls more steeply than assumed. A mystery can therefore be scientifically productive without requiring anything exotic. There is also the deeper issue of definition. What counts as a star belonging to a structure? Is a star still part of a disrupted dwarf galaxy after it becomes unbound but remains near the orbit? Does the total population include stars now smeared into the halo but chemically linked to the old system? If the answer is yes, then the stars are not gone. If the answer is no, then they may be treated as missing from that structure even while remaining present in the galaxy. The number 100,000 may therefore reflect a disagreement not only about detection, but about the identity of the population being counted. In this way, the number becomes a meeting point between physical reality and conceptual boundaries. Gravity, stellar evolution, dust, survey limits, and catalogue cuts all shape what can be seen. But the final act of counting also depends on where astronomers draw the edge of an object and what criteria they use for membership. A faint stream does not announce where it ends. A dissolving dwarf does not carry a sharp border. A halo population acquired long ago may still exist chemically, while no longer existing structurally as a distinct object. When a number is attached to such blurred boundaries, its interpretation remains unstable, even if the data are honest and the analysis careful. This is one reason why the phrase 100,000 vanished stars can be both misleading and useful. It is misleading because it suggests a direct subtraction of individually known stars from reality. It is useful because it points toward a real tension between what astronomers expect to find and what their best present methods recover. The tension may lie in observation, theory, or both. It may involve stars that are hidden, dispersed, misassigned, or statistically overcounted in earlier work. The number signals that something about the mapping of a population needs revision. That alone is enough to make it scientifically meaningful. Observations indicate that many of the strongest puzzles in faint halo astronomy arise from precisely this kind of numerical tension, where estimated populations, observed members, and theoretical expectations do not align perfectly. It remains uncertain in some specific cases whether the dominant cause is survey incompleteness, contamination, dynamical dispersal, or a flaw in the underlying model of the system's history. Yet the broad lesson is clear. A number in astronomy is not the final truth. It is a carefully constructed bridge between data and interpretation. In this region, then, 100,000 ceases to be a dramatic headline figure and becomes a tool for diagnosis. It asks what kind of count is being made, what assumptions built it, what system it refers to, and what kind of absence is actually under discussion. The mystery deepens not because the number is large, but because the number sits at the boundary between direct sight and inference, there, inside the act of measurement itself. Apparent loss becomes evidence of how much the universe still resists being reduced to a clean and final tally. At the deepest layer of this mystery, the question is no longer where the stars are in space alone, nor even how they behave, nor how surveys record them. The question becomes more fundamental. What does it mean, in astronomy, to say that something is missing? A star can be physically destroyed as an ordinary luminous star, but that is rare. A star can be hidden by dust, submerged in glare, or dropped below a survey threshold. It can be stretched out of a compact dwarf galaxy and diluted into a stream. It can phase mix into the halo until its original family is no longer obvious. It can be removed from a catalogue by better motion data or stricter classification. It can remain present in the galaxy while disappearing from a particular object, a particular list, or a particular expectation. The inward path arrives here, at the distinction between what is gone, what is hidden, and what is simply not yet fully known. This distinction matters because astronomy does not observe the universe directly in the ordinary sense. It interprets light and other signals through instruments, models, and statistical methods. The sky offers radiation. Science turns that radiation into positions, distances, motions, populations, and histories. At every stage, the translation is powerful but incomplete. It allows the structure of the Milky Way to be mapped, the remnants as ancient mergers to be traced, and faint stellar systems to be inferred from tiny excesses of light. Yet it also means that absence can enter the story at more than one level. Something may be absent from the data, absent from the interpretation, absent from the chosen definition of a system, or absent from physical reality itself. These are not the same kind of absence. The headline image of vanished stars suggests physical disappearance. It invites the mind to imagine points of light switched off or removed. The calmer scientific picture is more layered. In most plausible cases, especially in the halo and among faint dwarf remnants and streams. The stars have not ceased to exist. They have become difficult to gather into a simple narrative. Some are too faint for a given survey. Some are too spread out. Some are hidden among foreground stars. Some were counted too generously before cleaner data arrived. Some have drifted beyond the boundary of the structure to which they were first assigned. The mystery, therefore, reveals as much about the limits of categorization as about the stars themselves. This is not a weakness in astronomy. It is one of its deepest strengths that it can distinguish these levels of uncertainty and slowly reduce them. A modern astronomer does not stop at noticing a discrepancy. The discrepancy becomes the beginning of a more refined investigation. Better imaging tests completeness, improved motion data tests membership, spectroscopy tests common chemical origin, simulations test whether gravity could have spread the debris farther than expected, multi-wavelength observations test whether dust has hidden part of the population. Each method addresses a different kind of possible absence. Over time, the mystery does not usually vanish in a single stroke. It separates into components, and each component becomes clearer. In this sense, the missing stars serve as markers of incomplete knowledge rather than of impossible physics. They indicate that some part of the mapping from reality to record still needs adjustment. That adjustment may be observational, it may be dynamical, it may be conceptual. A stellar stream may be wider than assumed. A dwarf remnant may be less bound than hoped. A catalogue may have admitted too many uncertain members or excluded too many real ones. A model may have predicted a brighter visible population than an old metal-poor system can actually supply. The stars, meanwhile, continue their long existence or their quiet remnants within the galaxy, indifferent to the categories built around them. There is also a philosophical calm in this final layer. The universe does not owe clean boundaries to human thought. A dwarf galaxy can dissolve gradually into the halo without presenting a clear final moment when it stops being itself. A stream can fade into background without a sharp edge. A population can be partly visible, partly inferred, and partly uncertain all at once. Human language prefers distinct states such as present or absent, found or vanished. Cosmic structure often occupies the space between these terms. The more carefully astronomy looks, the more often it finds transitions rather than absolutes. That is why the Boötes Void ultimately belongs only to the outermost misunderstanding of the story. It is a memorable emptiness, but the true mystery lies much closer to the working methods of galactic astronomy. The problem is not that a giant hole in space has swallowed stars. The problem is that stars in fragile, ancient and diffuse populations do not remain arranged in ways that are easy to detect and define. The farther inward the path has moved, the less exotic the explanation has become, and the more subtle. The mystery survives not because it defies physics, but because ordinary physics acting over immense time produces structures that challenge simple counting. Observations indicate that the Milky Way continues to reveal new streams, new ultra-faint companions, and new complexities in the outer halo as surveys improve. It remains uncertain how many ancient stellar remnants have already become too diffuse for present methods to identify securely, and how many apparent shortfalls will be resolved by deeper data and better modelling. This uncertainty is not a void in knowledge so much as a moving frontier. Each improvement in measurement redraws the boundary between what is known and what is merely suggested. At the innermost point of the mystery, then, 100,000 vanished stars becomes a phrase that must be translated. It means that expectation and evidence do not yet fully align. It means that the line between a structure and its debris, between a secure member and a probable contaminant, between a visible population and an inferred one, is still under refinement. It means that astronomy is looking at something real but difficult. The lingering traces of how galaxies grow by taking in smaller systems and scattering their stars across the dark. The stars themselves likely remain what they have long been: ancient lights, dim remnants, faint giants, and quiet low-mass survivors moving through the Milky Way's outskirts. Some are hidden, some are redistributed, Some were never where the first interpretation placed them. A very few, by the rare ordinary laws of stellar life, have truly ended as luminous stars. But the larger mystery belongs not to sudden cosmic erasure. It belongs to the patient correction of human maps. In that correction, the sky becomes less dramatic and more profound. What seems at first like disappearance becomes evidence of dispersion, selection, obscuration, and incomplete knowledge slowly giving way to clearer understanding. The final inward truth is gentle. The universe has not emptied itself of these stars in any impossible way. It has only arranged them and concealed them more subtly than first thought. The mystery now settles into stillness. The great voids remain where galaxies are sparse, but they're no longer mistaken for the scene of missing stars. The Milky Way remains surrounded by faint companions, broken streams, and ancient halo populations, each one carrying the quiet memory of long gravitational change. Surveys continue to sharpen their maps. Dust continues to dim some paths of light. Old stars continue to drift through the outer galaxy, and some of them remain difficult to gather into a clean census. The sky has not offered a simple subtraction. It has offered layers of uncertainty, each one smaller and more precise than the dramatic story first suggests. In that calmer view, the 100,000 stars have not entered an impossible absence. Many are more likely dispersed than destroyed, hidden rather than erased, uncertain in membership rather than gone from existence. A number first treated as a mystery of loss becomes a sign of how delicate astronomical counting can be when the stars are faint, ancient, and spread across immense distances. The deeper lesson is not that the universe has broken its own rules. It is that the rules, working patiently through gravity, light, time, and imperfect observation, create patterns far subtler than human expectation first allows. So the final image is not of stars vanishing into nothing. It is of the galaxy holding them in altered forms and altered places, while human understanding slowly improves its reach. The darkness around them is real, but it is not empty of meaning. It is simply the space in which evidence remains thin, where motion has outlasted structure, and where the map is still catching up to the sky.